Now let's see how a non-terminating decimal be expressed in P by Q form. Or is it possible that a non-terminating decimal be expressed in P by Q form? That is, in a rational form such that P and Q belong to Z and Q not equal to 0. So I want to express a non-terminating, a never-ending decimal number into a decimal in the P by Q form, a rational number. So let's see how we can just do that, or is it possible to do that or not. For example, I take a non-terminating decimal denoted by x for 0.3 bar. Now the bar is what we know, which we have learnt in the lower classes, to be a repeating number which is denoted so on and so forth with a bar. So bar indicates that 3 repeats till infinite times. So 0.3 bar implies this can be indirectly written as 0.33333, so on and so forth. Now let's see if this number, which is never ending or non-terminating or ever recurring decimal, which can be expressed in the rational form P by Q, with P and Q belonging to Z and Q not equal to 0. So let's see if it's possible. So x is 0.3 bar, which can be written as 0.333 and so on and so forth till infinity. Then I multiply 10 on both sides so that I get this to be x times 10 is 0.333, which is also equally multiplied with 10 on both sides. So this equation is multiplied with 10 on both sides. So x times 10 is 10x, and 0.333 so on and so forth times 10 is 3.333, because this 0 makes the decimal shift to the right and 0 vanishes when the decimal shifts to the right as 3.333, so on and so forth. So I have two equations here, equation 1 and equation 2. So I have these two equations which I'm going to take out here. So with equation 2 being 10x equals 3.333, so on and so forth, and my equation 1, which is 0.33, so on and so forth, I try to subtract the two equations so that this, on subtracting, changes the sign and I get 10x minus x, which is 9x, and 3.333, so on and so forth, minus 0.333, so on and so forth, will exactly give me 3. The subtraction will make this as 3.00 and so on and so forth, because 3 minus 0 is 3, 3 minus 3 is 0, 3 minus 3 is 0, 3 minus 3 is 0, and so on and so forth, all zeros till infinite times. Therefore, this on further simplification reduces to 9x equals 3, which by taking the constant to the right gives me x equals 3 over 9, which is 3 1s, 3 3s. Therefore, x is 1 over 3. Therefore, my x, which is 0.3 bar, can be written as 1 by 3. So I finally understand that x, which was 0.3 bar or which was 0.333, so on until infinity, can be expressed in the form P by Q, with P being 1 and Q being 3, and both P and Q belong to Z and Q not equal to 0. Therefore, it is possible that every non-terminating decimal can be expressed in the P by Q form, the rational form, with two tests: test 1, PQ belonging to Z, test 2, Q not equal to 0. Now let's see what if the non-terminating decimal or the recurring decimal is with two decimal places. In the previous session, we have seen a number which has one decimal place, 0.3 bar. Suppose I have the bar for 2 digits. Let's see how we can construct, or how we can convert that into rational form. Or is it possible, or it is not possible, for construction is what we're going to investigate in this session. For example, I take my value of x, which is 2.69 bar. Suppose my bar is for 2 digits, then the only thing I do is I just try to expand this, repeating the bar all the times. And the secret behind this is to shift this decimal not by one place but to 2 places, because it is the repeating number which is taken into account every time we try to convert the non-terminating decimal into p by q form. So I have this to be the number which repeats is after every 2 digits, therefore the decimal has to shift twice on the right, which is possible by multiplying 100 on both sides, because if I multiply 10, the digit moves only 1 unit shift to the right, but if I multiply with 100, the 2 zeros make the decimal shift 2 units to the right. And therefore, when I multiply x with 100 on both sides, I get this to be this times of 100, and which on further simplification gives 100x equals 269.6969 and so on and so forth. And my original x, which is this, converts to be x equals 2.69696969. The reason behind putting the decimals same is that when we subtract, all the decimals should get vanished, and therefore in order to make the decimals equal, the only possibility is by multiplying 100 on both sides, so that here I can subtract so that all the decimal values vanish to 0. So after this, my next step is to subtract, so that 100x minus x is 99x, and 269 minus 2 is 267.69000000, and so on and so forth, is how it vanishes in the decimal part when we subtract through multiplying 100 on both sides. So I get this to be x equals 267 by 99 is how we get, and I can further simplify this to be 3 8s are 24, 3 9s are, and 3 33s. Therefore, this most simplified answer for this is 89 over 33. Therefore, my representation of 2.69 bar, which is a non-terminating decimal which repeats 696969, can be written in the rational form as 89 over 33. P and Q both belonging to integers and Q not equal to 0 is how I understand the connection of the non-terminating decimal, which is possible to be converted to P by Q form. Similarly, if I have a 3-digit repeating number, say for example I have x equals 1.413 bar, then I have the 3 digits which repeat on and on. Because there are 3 digits repeating, the concept of multiplying by 100 for 2 digits shifts to multiplying by 1000 on both sides, because 3 zeros make 3 digits shifted by the decimal to the right. This is how we understand accordingly through the number of digits which have the bar existing, the number of zeros which we multiply on both sides is how we understand the tricky concept. So now that we have seen representing the irrational numbers root 2, root 3, etc. on the number line, let's try to see if any real number can be represented on the number line in approximation exactly where it has to be located. So here my session is about representing real numbers on the number line. For example, I take the number x equals 2.6. Now it is very easy to locate the number x equal 2.6. Or say for example, I take x equals 3.7. I find 3.7 to be easily located on the number line, because if I have the number line with minus infinity, plus infinity, 0, 1, 2, 3, and 4, etc., then I find 3.7 approximately here. So how do we get this to be approximately on the right side is how we're going to discuss in the number line. So this representation of 3.7 is just because if I take a second number line which is extended with, which is zoomed out for between 3 and 4, I see that between 3 and 4 I have 10 different scales. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I get this to be 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.9. So between 3 and 4, I again subdivide the scale into 10 units, breaking up at each unit being 3.1, 3.2, 3.3, 4, 5, 6, 7, 8, 9, and 10. Is how I get this point, exactly the 3.7, which is located by using the second number line out here. So my 3.7 is located through subdividing the scale between 3 and 4 units into re-subdividing again into 10 different units, so that I can exactly locate 3.7 on the number line. Say I continue this with the number x1, which is 3.74. I would like to locate the number 3.74, which is again more approximate value than 3.7. So what do I do with this number line? I start with the first number line between 3 and 4 somewhere out here. Again I subdivide. I get between 3 and 4 10 different units, and again 3.74 lies between 3.73 and 3.75. The value on the left of 3.74 is 3.73, and the value on the right of 3.74 is 3.75. So what do? I pick between, and also this value is between 3.7 and 3.8. So this value of 3.74 lies in the region between 3.7 and 3.8. So this is the region where this value lies. Therefore, I try to again break up this interval into 10 subdivided intervals. Now let's see how the number 3.74 up to 2 decimal places be represented on the number line exactly through its subdivided interval. Now as we know that 3.74 lies between 3.7 and 3.8 in this interval of, we'll try to make a number line between 3.7 and 3.8 subdivided again into 10 different intervals. So we get this to be minus infinity to plus infinity of, I take 3.7 and 3.8 and I subdivide this into 10 different intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get this to be 3.71, 3.72, 3.73, 3.74, 3.75, 76, 77, 78, 79, and this is finally 3.8. So my 3.74 can clearly be identified to be out here, which is 3.74. is how we understand the subdividing of intervals through which we can reduce or zoom in and zoom out the real number line accordingly as the number of decimals increase or decrease. For example, I continue further with the new number x2, which is 3.742. Then I have my third decimal, which is 2, and I clearly have this number lying between 3.74 and 3.75. So I try to locate the region between 3.74 and 3.75, and I make a new number line breaking up with this, and I have my 3.74 divided into different subintervals 1, 2, 3, 4, 5, 6, 7, 8, 9, and then finally I get to be with 10th interval, which is 3.75. Now 3.741 lies here and 3.742 lies here. 743, 745, 746, 747, 748, 749, and 3.75 is what we get out here. Therefore, the number 3.742 is said to be exactly lying out here. So here is what I identify, and proceeding similarly, as the number of decimals increase, the number of number lines get zoomed in and zoomed out, and where again the subdivided intervals can make me locate exactly the number fixed located on the real number line. Therefore, finally, the learning outcome is that every real number can be represented on the number line, however big the number of decimals are. The successive magnification of the given decimals through the successive magnification of the number line will finally give us, through the first magnification, which gives me the value 3.7, the second magnification, which gives me the value 3.74, and my third magnification, which gives me the value 3.742, is how I identify that through different successive magnifications I can visualize and locate the given decimal values on the real number line. Successive magnification is possible for identifying the real numbers on the number line. Now let's see the different types of operations which are applicable in real numbers, mostly the rational numbers and irrational numbers, which play a vital role in simplification process. For example, I have two real numbers. Say my x is root 3 plus root 2 and my y is root 3 minus root 2, and I wanted to know clearly x is an irrational number and my y is also an irrational number. So now let's see what the product would yield in its simplification through operations using real number properties. So when I multiply the two irrational numbers x times y, I find that x being root 3 plus root 2 is substituted for x, and root 3 minus root 2 is substituted for y respectively in the product. Now clearly I identify that this is in the form a plus b times a minus b, which equals a square minus b square, as learnt in the lower classes. So a plus b times a minus b is a square minus b square. Therefore, root 3 plus root 2 times root 3 minus root 2 is root 3 square minus root 2 square, is what we get in the form of the product. So root and squares cancel. So root 3 square is 3 and root 2 whole square is 2. Therefore, my product xy is 3 minus 2, which is 1. Now clearly I identify that for two irrational numbers, when multiplied, is giving me a rational number. Moreover, it's an integer or a natural number or a whole number. So the product of two irrational numbers can yield a rational number, is how we identify the concept of rational numbers connected. Therefore, my outcome is product of two irrational numbers can yield a rational number. Therefore, product of two irrational numbers can yield a rational number, but it is not always true, because it is not always possible that two irrational numbers can yield a rational number. Only sometimes, when the formulas can be exactly applied, is how we understand the concept of product of two rational numbers yielding a rational number. What about two rational numbers when multiplied? The product of two rational numbers cannot yield an irrational number, because it is its own respective rational numbers when multiplied which always gives a rational number. But the only exception is two irrational numbers when multiplied may give a rational number, but two rational numbers when multiplied always gives a new rational number. Now let's see how a number root x for any x belonging to real numbers be represented on a number line. So I would like to represent root x on a number line for x being a positive real number. Of course, roots are defined only for positive real numbers. Now that in the previous session we have discussed about locating root 2, root 3, root 4, root 5, etc. using the square root diagram or the square root construction of a polygon, through which we can locate only using the geometrical concept for integers. If you have a fraction, say I have something like root of 4.9, which I would like to locate on the number line, then it becomes quite difficult. Or how I can measure the length, this root 4.9 on the distance, is what is the biggest challenge out here. Therefore, let's see in today's session about how we can represent a root of a real number on a number line. So imagine before this, we need to go through some construction process to understand the representation more better. For example, I take this to be the distance AB, which is some x units. Imagine my distance AB is x units, and from B, the line AB is extended further one more unit, so that the distance BC is 1 unit. So I have here AB is x units and BC is 1 unit, is what we get with the complete number line from A to C. Now let me say the midpoint of AC is at O. So here is the midpoint of the line AC, which exactly is at O. So O is the midpoint of the line segment AC, through which AO is equal to OC. Now, let's try to construct the different key factors in understanding on how we can identify root of x using the number line. Say for example, I take the length OC or OA and then try to construct a semicircle using the radius from compass O to A. So with radius as OA, here is my semicircle, the radius being OA. Now let me just draw a perpendicular from B so that it cuts 90 degrees and passing through B. So I drop a perpendicular onto B, which cuts the semicircle, say at some point D. So D is the point where the line, the perpendicular line passing through B, cuts the semicircle at D. Let me join OD. So here I have a right angle triangle OBD through this construction. Now, how do I measure the distance OB? I would like to measure the distance OB. So I see clearly that OB is OC minus BC. So the distance OB is the entire radius minus this, which gives me the distance OB. Therefore, my OC is the radius which I need to find out here. So let's see what will be the radius OC. Now, because my diameter AC is x plus 1, because it accounts to x and 1 unit, my whole distance AC is x plus 1. So x plus 1 being the diameter, the radius OC is exactly half of AC, and therefore it is exactly half of x plus 1, because AC is already substituted to be x plus 1, is already simplified to be x plus 1. Therefore, my OC is x plus 1 by 2. So I just substitute this to be x plus 1 by 2 minus BC, which is 1. Substituting for OC and BC respectively, I get this on further simplification to be x plus 1 minus 2 by 2, and this gives me x minus 1 by 2. Therefore, my distance OB is x minus 1 by 2. Therefore, my distance OB is x minus 1 by 2, and my distance OD is nothing but distance OA, which is already identified to be half of this. So OC is nothing but OA, and the distance OD is equal to distance OA, which is already identified to be x plus 1 by 2, because this and this and this are the radius. The radii of the circle are equal. Therefore, my OB is x minus 1 by 2, and my OD, which is simplified out here, is x plus 1 by 2. Now I have OB and OD through which I am going to find the length BD. To find the length BD, we are going to use the triangle, right angle triangle OBD, and then through Pythagoras theorem, let's try to find the length BD. So to find BD, I take right angled triangle OBD, in which I have OD square equals OB square plus BD square, using the Pythagoras theorem. Now, OD square is x plus 1 by 2 whole square, because I have OD which is substituted out here. My OB is x minus 1 by 2 whole square, which on substitution gives me this, plus BD square. So I take BD square to the left and all the terms to the right and simplify, so that I get this to be BD square equals x plus 1 by 2 whole square minus x minus 1 by 2 whole square. Now this on further expansion gives me x plus 1 whole square by 4 minus x minus 1 whole square by 4. To be continued, it has x plus 1 whole square by 4 minus x minus 1 whole square by 4, which can be simplified using the LCM. Therefore, I get this to be BD square equals x plus 1 whole square minus x minus 1 whole square by 4, which on further simplification gives a square plus 2ab plus b square minus a square minus 2ab plus b square by 4, which on further simplification gives x square plus 2x plus 1 minus x square plus 2x minus 1 whole by 4. This gets cancelled and 1 gets cancelled, and we have 4x by 4, which is x. Therefore, my BD square is x, which implies the length BD is root x units. So my length BD is root x units is how we construct using this geometrical process. So finally I get my length BD, which is root x units. So using this BD, finally I try to identify that using any real number x on this dimension of AB, I can construct root of that real number through this distance. The derived formula, which already gives the length BD, is indirectly the square root of this number, is how we identify the geometrical process out here. Let's see how the root x concept can be applied in real life for constructing the root of 5.3, which is an irrational number without an integer. So square root diagram doesn't help us, the spiral square root doesn't help us in the process. So let's use the previous concept of constructing through root x from x. Now as I take the given number, which is root 5.3, which has to be located on the number line, I clearly find that the x value out here is 5.3 from the root x. So we first pick the value of x, and then in step 1 of the construction, we take the distance 5.3 out here. So let AB be the base constructed with exactly 5.3 units. It can be centimeters, it can be meters, but take the measurement of 5.3 as the base of AB. Extend this line so that we take the distance of 1 unit and cut on the number line so that this acts as 1 unit. So this line segment AC has two segments, AB and BC, with the length AB equals 5.3 units and the length BC equals 1 unit. So which totally accounts to 6.3 units. Now I have the AC, which is AB plus BC, and 5.3 plus 1, which is 6.3 units, is the diameter of the semicircle. Now using this complete line segment, I will try to find the midpoint of AC. So midpoint of AC, which I mark as O, is assumed to be the center of the circle, and let's see what is the distance AO or OC. Is O, and AO equals OC, which is half of AC, because the distance this is half of the entire length, and AC being 6.3 will be half of 6.3, which is 2 3s are 6, 2 1s are 2, 2 5s 10. So this is 3.15 units. So my AO is 3.15 units, and the distance AO, which is 3.15 units, is cut. Take the compass at A and cut a distance of 3.15 units, and then we get the midpoint. Or take the scale and mark exactly the middle point. There are different ways through which you can do through the perpendicular bisector, which also gives us exactly the midpoint. Take more than half, cut an arc, cut an arc, cut an arc, cut an arc, and we get the midpoint out here for the line AC by fixing at A and C and cutting the arcs. So once we get the midpoint O, I assume that my distance AO is nothing but the distance OC, the radii, and then that is equal to 3.15 units. Now take the center and draw a semicircle with OA as the radius. So the next construction is to draw a semicircle in this manner. So once a semicircle is drawn through O with the radius as OC or OA, I get a semicircle in this manner. Now from here, the next step is to drop a perpendicular from B. So put the protractor at B and make a 90 degrees through the line AC. So with the base as AC and angled at B, I get 90 degrees, which is extended to cut the circle at D. So here I have my distance D, which is from B and which cuts the semicircle exactly out there. So this is how I get the point D, by extending the line to cut the semicircle. Now once I get this, it's all about joining D. And the property which we have done in the previous session is that if this is x, this will be root x. So if this distance is 5.3 units, then the distance which you cut at semicircle from B will obviously be root 5.3 units, is what we have derived in the previous session. This length being x, this length gives us root x, is what is derived. And hence, this length being 5.3 units has to obviously give us this distance BD, root 5.3 units. And hence, this distance, again taken on the number line, will cut from 0, take this distance and cut here, then I get this to be root 5.3 unit. And that is how we can mark it on the number line, where root 5.3 units, which is the measure of this length, can be represented on any number line. So root x for x belonging to R plus can be represented on a number line using the semicircle geometrical concept properties. Now next, let's see how to rationalize the part of irrational numbers. So the concept here is rationalizing the irrational numbers. Part of. Let's see how this can be done out there. So for example, I have a number 3 by root 12. And I would like to rationalize this denominator because my denominator is an irrational number which I would like to rationalize. So in order that I rationalize, I understand that its root has to be removed. Rationalizing the root is possible only when the root vanishes. Therefore, in order that root 12 has to vanish, let's try to see how this is possible. It's very simple, because when you have the number 3 by root 12, I can simply rationalize the denominator by multiplying and dividing the same rational number besides the given number. So here is the root 12, so I multiply and equally divide so that it doesn't disturb the justification of the mathematical value out there. So once the root 12 is multiplied and divided, I get this to be 3 times root 12, which is 3 root 12, and root 12 times root 12 is already known with the property root x times root x is root x whole square, which is x, and therefore root 12 times root 12 must be 12, and therefore this can be simplified as 3 1s 3 4s root 12 by 4. This can also be further simplified by taking root 12, which is 4 times 3 and by 4, so that this can be split as root 4 times root 3 by 4, because root AB is root A times root B. Every factor can be split in the root provided it is in multiplication. Root of A plus B is not equal to root A plus root B. The splitting of roots is possible only in division and multiplication. So I have root 4, which is 2 times this by 4, which can be further simplified as 2 once and twice, so that the final answer is root 3 over 2. So interestingly, the irrational number which was in the denominator jumps to the numerator. So we have now an irrational number in the numerator, but there is no irrational number in the denominator. This is how we rationalize through either the numerator or the denominator, depending on the question given. Rationalizing the numerator and the denominator is very much possible, as witnessed with this example problem. Let's see one more example through which we understand the rationalizing concept of an irrational number more better and more stronger. For example, I have my x, which is 1 by root 11 minus root 9, or I have this 2 by root 11 minus root 9, and I clearly see that the denominator has irrational numbers and the numerator has strictly a rational number. So my question out here is, how do we rationalize the denominator, which is irrational presently? So let's see how we can rationalize the denominator out here. So in order that I rationalize this denominator, the concept in case of two added or subtracted numbers is that I multiply and divide the same number with opposite sign in between. That is, when I have 2 by root 11 minus root 9, then I multiply and divide with the same irrational numbers but with opposite sign. If I have minus out here in the given question, I have plus, which I multiply and divide. If I have plus in the given question, I put the opposite sign minus in the numerator and denominator. Is how we understand the general rule which applies for any problem where the denominator or numerator is rationalized in this format. So I multiply and divide with this, which gives me 2 times of root 11 plus root 9 by root 11 minus root 9 times root 11 plus root 9 is how we get it. Now clearly I see here that this is root 11 plus root 9 by, this is clearly in the form a minus b into a plus b, which we know through the formula that a minus b times a plus b is a square minus b square. And therefore, this minus this into this plus this is a square minus b square. And finally, this comes out to be 2 times root 11 plus root 9 by square and root both get cancelled, and I get this to be 11 minus 9. And therefore, this comes out to be 2 times root 11 plus root 9, of course, is 3. Though given in the question in unsimplified form, I can substitute this root 9 to be a perfect square to be 3, and 11 minus 9 is 2. Therefore, I see that the denominator is rationalized finally. The denominator which was in roots is no more with any root form. And further, I can simplify this to bring into the more simplified form so that I get my x as root 11 plus 3 is how we get for this. And thus, we finally understand that denominator is finally rationalized. Rationalizing the denominator or the numerator for any given number is possible. Exponents connected with real numbers. Now that we have seen different properties like rationalizing using a plus b into a minus b, which is a square minus b square, and various other properties, now we are going to enter into connecting the real numbers with exponent properties. Laws of exponents, laws of indices is what we are going to talk about. Laws of exponents in real numbers. So let's see how they are collaborated or interconnected with each other. Without the use of laws of exponents, we cannot proceed further by operating the real numbers, is how we understand this session being important and to be learnt in the number system, in the topic of number system. Now we know that the laws of indices are a power m times a power n is a power m plus n, the most famous law of index which you have learned in the lower classes. Similarly, the next law of index is a power m by a power n, which is a power m minus n. This is how we understand this. So based on these two properties, let's see how we can simplify some different examples where real numbers are given in this form. For example, I have a question which says simplify the real numbers which are expressed in the form 5th root of 7 cube root of 7 into root 49. So let's see how we can simplify this strictly using the laws of exponents. Now clearly I see that this can be simplified initially by extracting the roots. So because it's in the 5th root of 7, we understand that nth root of a is a power 1 by n, and hence 5th root of 7 is 7 power 1 by 5, and root 49, which is 7 because root of 7 square, and cube root of 7 is 7 power 1 by 3. So basically when we discuss about laws of exponents, we think of making all the bases equal is the rule we need to identify. So because the given question has different bases, my first target was to make all the bases 7 equal. Now I clearly see that this satisfies the property number 2, that is a power m by a power n is a power m minus n. So replacing a by 7, I get the second law of index, which is a power m minus n, is how we understand this. Times 7, never to be forgotten. And here I get this by further simplifying through LCM. I get 7 power 15 3 minus 5 times of 7. So I get this to be 7 power this times 7, which on further simplification gives 7 power negative 2 over 15 times 7, which can be written as 7 power 1. 3 minus 5 is minus 2 over 15 times 7 power 1. Now clearly I see this with index number 1, which is a power m times a power n is a power m plus n. Therefore this times this gives me 7 power minus 2 times 15 plus 1. When the two bases are equal, the powers are added in the product, which on further simplification gives minus 2 plus 15, which on further simplification gives 13 over 15. And therefore my complete simplified process of this problem is 7 power 13 by 15, or this can also be written as 15th root of 7 power 13. So simplifying the given problem is based on the laws of exponents if the problem gives the real numbers expressed in exponent form. Laws of exponents connected with real numbers.